Hello viewers, welcome to Ansys-Tutor. In the previous 3 videos, I had shown the very basics of available sketching tools in ANSYS Design Modeler. In this video, we would take a case of pipe flow problem demonstration. From this tutorial you would be familiar with all the process flow involved in the fluid flow analysis. Here is the problem statement. It is a 20 mm diameter pipe, its length is 100 mm. The water is entering into it at a velocity of 0.0005 meter per second. You need to find the velocity variation in the pipe. At first, open the ANSYS Workbench program. Then select the ANSYS Fluid Flow from the toolbox, double-click on it, or alternatively drag it into the project schematic window. Click on the geometry. Now you would be able to see a properties table in the right side of the window. Scroll down in it to the advanced properties. In this choose the analysis type to 2D, as we are going to do a 2D analysis. Now, right-click on geometry. Select the second option, that is ANSYS Design Modeler, to create the geometry. Change the default units to millimeter. Select the XY plane, click on the Z to make the sketch normal to the screen. Switch to Sketching tab. Select the rectangle from the Draw toolbar. Put dimensions to the rectangle. Now, the sketch is complete. We need to convert this sketch to a 2D geometry. For this we need to go to the Concepts menu. Here we can get the option Surface from Sketches. Using this option we will convert the sketch to a 2D geometry. Click on the surface body from the tree outline. Now the details of the surface body table appears in the left corner. In this table, change the body type to fluid. So the meshing software will mesh it as a fluid domain. Now proceed for meshing the geometry. Open the Meshing Workbench window. By default, ANSYS Meshing has set some default mesh sizes for this geometry. So let's generate the mesh using default mesh settings. This is the default generated mesh. Now we gonna modify the default mesh setting to further decrease the mesh size. Let's change the default element size and generate the mesh. Check the mesh statistics to see the generated nodes and elements. Let's check the aspect ratio of the generated meshed cells. For this, you need to select Display Style in Details of Mesh. You can see, the meshed cells are not distributed properly in some regions. For this we need to change another setting, that is adaptive meshing. We need to turn on adaptive sizing to distribute the mesh uniformly throughout the geometry. Now all the meshed cells are distributed uniformly. It now a structured mesh. You can also check the skewness of the meshed cells using the display style. We would discuss more about the meshing and how to check the quality of the mesh and its importance in our upcoming videos. Now, we would select the boundary to name it. For this we need to choose the selection tools. Here are the selection tools. Vortex selection, edge selection, surface selection and body selection options are available here. From this, select the edge selection option and select the edges in the geometry. Select the edge. Then right-click, then select Create Named Selection from the menu. Now put a name for the boundary surface. We had denoted the bottom edge of the rectangle as axis as it's an axisymmetric problem. Similarly, name the other boundary surfaces. All the named boundaries are listed in the tree outline under named selection. You should cross-check these named selections once. As if a boundary is named twice, then it might cause error on updation. Right-click on Mesh and select Update. It will update the generated mesh with the Fluent CFD solver. You would also receive an info message regarding this. Close the meshing and go to Workbench window to open the Fluent for CFD solver setup. Right-click on Setup and then select Edit. Now, a Fluent launcher window will appear. It will ask regarding whether you want to set single precision or double precision solver, number of CPU processor to employ, series and parallel solver, etc. We will discuss more regarding this in our upcoming videos. For the current simulation, select the double precision model and press OK. This is the ANSYS Fluent solver window. Here we would put all the boundary conditions and will do necessary setups, which is required for the analysis. As it's an axisymmetric analysis, so you need to select axisymmetric 2D space. Check the loaded mesh quality. Select the required flow model from the list of available models. In the current problem, the Reynolds number is 9.952, which is less than the Reynolds number 2300 for pipe flow case. So a laminar viscous model is selected for this analysis. Now load the fluid material from the Fluent database. You could also change the material properties as per your requirement. For the current simulation, let's take default water as the fluid material. You could only see the necessary material properties as per the selected model. You can also add the solid materials from the Fluent database by selecting material type to solid. Now assign the material to the fluid domain meshed body. Click the Operating Conditions tab. Put the operating pressure. Atmospheric pressure is the default operating pressure. Switch to boundary conditions, select the boundary and put the required boundary conditions. As per the named selections, the solver assigns the boundary conditions type by itself. You can change these boundary conditions. Select velocity inlet boundary condition at the inlet and put the inlet velocity of 0.0005 meter per second. Press OK. This boundary has been created by the solver, so no need to do any changes to this interior. Keep the default pressure outlet boundary type for the outlet boundary. Press OK. As the pipe is a stationary one, so no need to change the default pipe wall boundary settings. Press OK. Now go to Solution Methods and select Simple in the Pressure Velocity Coupling Scheme. Simple defined as the semi-implicit method for pressure-linked equations. It means to instruct the solver to use simple algorithm to solve the numerical problem. To know about the details about how this algorithm works, see the links in the descriptions. Now go to Monitors. Select the residuals. Decrease the residuals up to 10 to the power -6 for a better solution accuracy. The iteration process gonna be continue until all the numerical iterations achieve this residuals value. Press OK. Click on Initialization. Select the standard initialization. Select Compute from any boundary, then press Initialize to finish the solver setup process. Click on Run Calculations. Set the number of iteration to run and start the iteration process by clicking on Calculate. Calculation is complete now. This is because all the numerical equations reached the set residual value of 10 to the power -6. Hence the solution is converged now. Now check the results. See the variations of velocity as a form of a contour. It can be seen that the velocity is maximum at near the central axis and decreases towards the pipe wall. Similarly, check the contour for pressure. Let's check the velocity variations along the central axis. For this, go to Plots, select XY plot. Select velocity in y-axis function and direction vector in x-axis. Select the axis and click on Plot. You can also modify the color of the curve and type of marker for this plot. Now close the meshing and proceed for CFD post-processing. This is the ANSYS CFD post-processing workbench window. Insert a contour to observe the velocity variation. We would also create the contour for the full pipe body. This denotes the color bands for the contour. For more number of color band you can increase the number. You can also modify the default legend view. To show the contour for the full pipe body, you need to apply a reflection to the contour. Now let's create the velocity vector for the domain. Similarly, create reflection of the velocity vector to show the velocity vector in full pipe domain. You can also modify the velocity vector symbols and sizes. Let's check the streamlines. Now animate the flow in this pipe domain using quick animation option. You can also modify the symbol size and spacing. To save the animation file, mark the Save Movie option, choose the file save location. Click on the infinity symbol to turn off the Repeat Forever option. To modify the video output quality, click on Options. Enable the white background option if you want the animation to play with a white background. Select the video quality from the image size. Now after setting up, press the play button to record the animation. Go to Location menu. Then insert a line. This line will be used to plot the velocity variations along the radial direction. Enter the coordinates of the line. Let the line be created at the middle length. Insert a chart to plot the velocity variation graph. In the Details of Chart, switch to the Data Series tab. Select the line as the location. Select Y length and X axis to see the radial variation of velocity. With this we conclude this demonstration. In our next tutorial video, what you want to see, please comment below. If you like this video, then please hit the like button. If you have not subscribed to our channel, then please subscribe. It will motivate us to bring such tutorial videos for you. Stay home, stay safe. Thank you.